Hello students, in this video we will solve a question from CSIR NET December 2024. We have a particle of mass m. It is bound in one dimension by the potential V of x is equal to V naught delta of x with V naught less than 0, V naught is negative. If the probability of finding it in the region modulus of x less than a is 0.25, then what is the value of a? So the given potential, it is attractive Dirac delta potential. We have V is equal to V naught times delta of x, where this V naught is negative. So this is equal to 0 for x not equal to 0, and it is equal to minus infinity for x equal to 0. As you can see in the graph, V of x is equal to minus infinity at x equal to 0, and at all the other points V is equal to 0. Now the wave function for attractive Dirac delta potential is root alpha e raised to minus alpha modulus of x, where alpha is equal to minus m V naught divided by h bar squared, or alpha is equal to root of minus 2me divided by h bar squared. Now do not think that there is a negative sign inside the root, because E is negative. E is negative for bound state. Why do we say that? Because we have the condition for bound state. Condition for bound state is E less than V of x tends to plus or minus infinity. Now V when x tends to plus or minus infinity is 0. Therefore we have E less than 0. Therefore for bound state E must be negative, and if E is negative, negative multiplied by negative will become positive, and alpha is positive. Here V naught is negative, negative times negative is positive. So alpha is positive and its value is minus m V naught divided by h bar squared, or you can say it is equal to square root of minus 2me divided by h bar squared. So these three things, the wave function, value of alpha, these three things, if you remember, then you can solve the problems of attractive Dirac delta potential. Now you can derive these things, but it will take some time. You do not have the luxury to do that during the exam. So let's derive these things now. How are we able to get this wave function? Let's see. So the Schrodinger equation is in one dimension d square psi upon dx square plus 2m upon h bar squared times e minus v psi is equal to 0. Now for x not equal to 0, what is the value of v? V is 0. It is here. V is 0 when x not equal to 0. Therefore our equation becomes d square psi upon dx square plus, now I am naming 2me upon h bar squared. Is this negative quantity or positive? This is negative, because E is negative for bound state. Now if I put a negative sign here, then it will make this positive. So now it is positive. Minus 2me upon h bar squared is positive quantity now, and I am saying this is equal to square of alpha. Then I will have alpha is equal to root of minus 2me divided by h bar squared. Then the equation becomes d square psi upon dx square. Instead of 2me upon h bar squared, now I will write minus alpha squared. Minus alpha squared psi, this is equal to 0. Now this is a very standard differential equation, and the solution of it is in the form c1 e raised to alpha x plus c2 e raised to minus alpha x. So this is the solution. In this region, what happens when x tends to infinity? When x is tending to infinity, this e raised to alpha x, it tends to infinity, and therefore psi tends to infinity. But is this acceptable? This is not. Why? Because we are saying that the particle is in infinitely far region with finite probability, which is not physically acceptable. Therefore, we say that for x greater than 0 region, C1 must be 0. C1 must be 0. So if we write the wave function for x greater than 0 region, let us name it psi2, then psi2 will be equal to C2 e raised to minus alpha x. Because we cannot have psi tending to infinity when x tending to infinity, we make C1 equal to 0 in the x greater than 0 region, and therefore the wave function in that region is C2 e raised to minus alpha x. C2 psi2 is equal to C2 e raised to minus alpha x. Now consider the region x less than 0. In this region, if x is tending to minus infinity, what happens? If x is tending to minus infinity, then e raised to minus alpha x, this will tend to infinity. So for x tending to minus infinity, psi is tending to infinity. Therefore, in the x less than 0 region, we need C2 to be 0. C2 must be 0, which means the wave function in the x less than 0 region, psi1, this must be C1 e raised to alpha x. So in this region, we need psi1 to be equal to C1 e raised to alpha x. Now there is a property of wave function that it must be continuous at all points. Therefore, from the property of continuity of psi must be continuous at all points. We say that psi1 of x equal to 0 minus, this must be equal to psi2 at x equal to 0 plus. That is, we are saying that if we approach to x equal to 0 from right side, or if we approach from x equal to 0 from left side, in both the cases psi at 0 must be same. So that's why we are writing like this. 0 minus means we are approaching to 0 from the left side of the axis, and 0 plus means we are approaching to 0 from right side of the axis. So both of the values must be same. The wave function must be same in both the cases because psi is continuous. That's the property of wave function. This implies C1 e raised to alpha 0 is equal to C2 e raised to minus alpha 0, which implies C1 is equal to C2. Let's say this is C, then the wave function becomes, for x less than 0, psi1 is C1 e raised to alpha x. Now we have found C1 is equal to C. So we can write psi is equal to C e raised to alpha x for x less than 0. And what is for x greater than 0? For x greater than 0, we have wave function C2 e raised to minus alpha x, and C2 is C. Therefore, this is C e raised to minus alpha x for x greater than 0. Now this can be written using the modulus as C e raised to minus alpha modulus of x, because modulus of x is equal to x for x greater than 0, and it is minus x for x less than 0. Now to get the value of C, what you can do is you can use the normalization condition. So what is normalization condition? If you integrate psi star psi over all space, then this must be equal to 1. This is the normalization condition. Now psi is a real function, so you have to just square. And you can see psi is even function, therefore this is also even function. So you can make use of the property of even functions and write 2 times integral 0 to infinity psi square dx. This is equal to 1, which implies 2 times integral 0 to infinity c square times e raised to minus 2 alpha. Now we will not write modulus because from 0 to infinity all the values of x is positive, and for positive values of x we have modulus of x is equal to simply x. Therefore we will write x here dx. Now we have to do this integration. This is equal to 1. This implies 2 times, when you do this integration you will get 1 by minus 2 alpha e raised to minus 2 alpha x. You have to evaluate this from 0 to infinity. This is equal to 1. This implies 2 gets cancelled, minus c square by alpha times e raised to minus 2 alpha infinity is 0 minus e raised to minus 2 alpha 0 is 1. This is equal to 1. From here c square by alpha is equal to 1, which implies c is equal to root alpha. So when you substitute this back to the wave function here, we will get psi is equal to root alpha e raised to minus alpha modulus of x. Now let's make use of another property, that the derivative of psi with respect to x, this is discontinuous at a point, is discontinuous at a point if potential, if there is a change, an infinite change in potential at that point. Now in this problem you can see that there is an infinite change in potential at x equal to 0. At x equal to 0 there is an infinite change in potential. It is suddenly going to minus infinity, and therefore del psi by del x will be discontinuous at x equal to 0. Del psi by del x is discontinuous at x equal to 0. Since Schrodinger equation contains d square psi upon dx square, if we integrate Schrodinger equation, then we get an equation with terms del psi by del x. So we start with Schrodinger equation, which is d square psi upon dx square plus 2m upon h bar squared e minus v of x psi is equal to 0. Now we integrate near x equal to 0, because at x equal to 0 we have discontinuity in del psi by del x. When we integrate we will get d psi by dx at x equal to 0 plus, so we are considering a very small interval near x equal to 0, that is from 0 minus to 0 plus. In this range we are integrating. Now 0 minus means a very small quantity which is left side to 0. That means it can be 0.00000, negative 0.000001, some value like this. a very small value which is near to 0, and 0 plus means a very small value which is greater than 0, that is 0 plus epsilon, where epsilon is very less than 1. You can say 0 plus is equal to 0 plus epsilon, where epsilon is very less than 1. So when we do this integration here x equal to 0 within the range 0 minus to 0 plus, then we will get d psi by dx at x equal to 0 plus. You have to evaluate this derivative at x equal to 0 plus, minus d psi by dx evaluated at x equal to 0 minus, plus 2m upon h bar squared integral x equal to 0 minus to x equal to 0 plus e minus. Now let's substitute v of x. V of x is v naught delta x dx. Now if you integrate a function and the limits of the function are very close, then that function integrated will give you 0. So integral 0 plus 0 minus to 0 plus of e dx, this is equal to 0 because the limits are very close. But Dirac delta is a special case. 0 minus to 0 plus integral v naught minus v naught Dirac delta dx. This is not 0 because the peak point of Dirac delta, which is x equal to 0, is lying within the limits of the integral, and therefore this will give you, there is psi here, I forgot to write it here. This is psi of x. So this will be equal to, this integral will be equal to psi of 0. So our equation becomes d by dx of, for positive values of x we have to take x equal to, modulus of x is x, so we will write c raised to minus alpha x evaluated at x equal to 0 plus, minus, for negative values of x you will take the wave function as c raised to alpha x. This is to be evaluated at x equal to 0 minus, and when you do this integration, that is 0, but from second integration you have psi of 0. So this is 0 plus 2m upon h bar square is outside, times v naught with a minus sign. So there is minus v naught also here, minus v naught times psi of x, psi of 0, and this is equal to 0. Here is 0. Therefore from here we are getting c times minus alpha e raised to minus alpha times 0 minus c times alpha e raised to alpha 0 minus 2m v naught upon h bar squared. Psi of 0 is c e raised to minus alpha modulus of 0, which is 1. This is equal to 0. C gets cancelled from all the terms. From here we have, this is equal to 1, this is also equal to 1. So from here we have minus 2 alpha is equal to 2m v naught upon h bar square, which gives alpha is equal to minus m v naught upon h bar square. Now there is a value of alpha here which is minus 2me divided by h bar square under root. and there is a value of alpha here minus m v naught upon h bar squared. If you equate these two, you can get the energy. Energy will be equal to minus m v naught squared upon h bar squared. Now in this expression for energy, you cannot see any n here. Therefore, we can say there is only one bound state because there is no presence of n. Like in the case of harmonic oscillator, you have energy equal to n plus 1 by 2 h cross omega. So there is n here. So there are multiple bound states. But in this case, you have no n present in the equation of energy. So therefore, we say there is only one bound state possible for attractive Dirac delta potential. Particle under attractive Dirac delta potential. Actually, there is a 2 here. You can check it by equating the two values of alpha and solve for E. It will be minus m v naught square divided by 2h bar squared. Now let us come back to the question. So all of these were derivations which are not required for solving this question. We only need to know the wave function psi and the value of alpha, which is equal to minus m v naught upon h bar squared. So we are given the probability of finding the particle in the region modulus of x less than a is 0.25. So it is given probability is when you integrate from the range is modulus of x less than a. Modulus of x less than a means x is in between minus a and plus a. So the integration limits are from minus a to plus a, and to get the probability, what you do is you integrate modulus of psi square dx within the limits, and this is given to be equal to 0.25. This implies integral minus a to plus a. Now we have already seen that psi is even function, so you can make property of even function because modulus of psi square is also even. Therefore we can write here integral 0 to a 2 times integral 0 to a modulus of psi square dx. This is equal to 0.25. Now let us substitute the value of modulus of psi squared. So this implies 2 times integral root of alpha squared e raised to minus 2 alpha x dx. This is equal to 0.25. From here we have limits are from 0 to a. Therefore we have 2 alpha times e raised to minus 2 alpha a minus e raised to minus 2 alpha 0 divided by minus 2 alpha is equal to 0.25. This implies 2 alpha gets cancelled. When you take the minus sign inside, then we will get 1 minus e raised to minus 2 alpha a. This is equal to 1 by 4. 0.25 can be written as 1 by 4. This implies 1 minus 1 by 4 is equal to e raised to minus 2 alpha a, which gives 3 by 4 is equal to e raised to minus 2 alpha a, which implies ln of 3 by 4. This is equal to minus 2 alpha a. Now let us substitute the value of alpha. Alpha is equal to minus m v naught upon h bar squared. So if you put this here, then we will get minus 2 times m v naught upon h bar squared times a. This is equal to ln of 3 by 4. Here is a minus. So both negative signs gets cancelled. From here we have a is equal to h bar squared divided by 2 m v naught times ln of 3 by 4. Therefore the value of a is h cut square divided by 2 m v naught ln of 3 by 4. H cut square divided by 2 m v naught ln of 3 by 4. Option 2 is the correct answer here.